let's jump into the next technique, which is by far the most popular technique in the world today as far as how to implement functional testing, and that's instrumentation-based equipment. The idea behind instrumentation-based equipment is you have a PC that controls the tester, but you can put all the kind of different cards in the PC so that your DVM and counter timer and all these other instruments that are usually in a rack are actually in the PC now. Now, if you don't have room, then you can obviously have rack mount equipment too. But this kind of equipment from companies like Agilent and National Instruments is very handy in that they come with their own software drivers and they come with their own software operating systems, so that you can just buy the software, be it LabVIEW, VEE, whatever it is, and it will have its own drivers for all these instruments. Digital, analog, STEM, measure, whatever you need to do. The last segment here, as far as learning the different techniques for functional testing, is called quiescent current. Actually, this one's usually used in conjunction with other techniques. It's not a great standalone technique, but it's such a powerful technique we might use that in the ATE-based or emulation-based testers. So this is just one technique that makes a lot of sense and might prove to be very powerful for you. The name comes from the power current is often called IDD. The I for current, and then VCC, VDD, that's your power supply, so IDD would be your power current. So the Q just stands for quiescent. So in other words, I want the board to be quiet. I want it to be in a resting position. And when it's in that resting position, I need to measure that current coming out of the power supply feeding my board. There's several techniques for this. Let me show you a few of those techniques. Some are difficult depending on the kind of power that you have. But certainly, if you have a power supply with current measurement capabilities, this becomes extremely simple. So if you can do that, great. If not, then you might have to build some hardware into your fixture in order to make this measurement. The idea is that at a quiescent state, my current should be extremely low. So the idea is I'll power up my board, and hopefully I might have to use a bed of nails technique, but hopefully I have access to all the ways to I can disable all the devices, so all the devices are asleep. The microprocessor isn't out talking on the buses or asking the prom to send it data. They are asleep. They are quiescent. And so my current should be very, very low. All I got is a leakage current going through the caps and finishes charging caps. I should have almost no current. So if my current's too high, I probably have a device that's switching and trying to turn on, or the wrong kind of value device, or some other kind of defect that I can tell. So I don't want the current to be too low. I don't want it to be too high. So you have a little bandwidth of where the current should be. So I'm kind of showing that at maybe around 150 milliamps. But then maybe you can enable a chip, so you can get it to start booting up, for example. And after it finishes booting, you can look at, say, U1 and U2 as a cluster, and I should have this kind of current. And then the current will go up a little higher when I enable U3. Then maybe I disable some of those and I measure the current with only one or two other devices. That is hard to do because you have to have a bed of nails fixture and be able to disable each one of these devices. But when you can, this is a very good test.